a gravitational simulation. A gravitational simulation walkthrough. Let me update the title on the stream here. Gravitation simulation walkthrough. I assume I need to. All changes saved. Okay, so in Unreal they have their own really fantastic gravity pre-baked and built in, and it works fantastic for most things that you would want. What is going on? Oh, it's because the character mesh is hitting, and they have the angular rotate or the angular velocity dampened. But so they've got their own gravity, and I've just started up a very simple project here. And to get the gravity turned on, all you do is drag out a cube, and then on the cube you can scroll down, and in the physics area you can turn on simulate physics and enable gravity and leave everything else the same, and gravity is on and the physics is simulating correctly. There are some downsides, however. If you want gravity to go the other direction, there's nothing obviously here, and there is a way to do that, which I'll show very quickly. There is a way to change the gravity for a character. So I've gone ahead and created a character, and I just put this sphere in the character for visibility. You can see the viewport, I just dropped it in there. And what I can show is that if you come to the character movement component here, you can change the gravity scale to 0, which will give us a no movement. Still simulating physics, but no gravitational movement. Or you can even go in and change it again in the character movement component here. You can change the gravity scale to negative. And it doesn't have to be between 1 and -1. It can be larger numbers if you want it to go faster. So that's good if you want gravity to completely reverse. But what if you don't? What if you want the gravity to, say, go left or right? What if you want the gravity to go at a diagonal or even towards another object, maybe a platform that has artificial gravity like a spaceship? So this stream I'm going to talk a little bit about how to simulate that very easily for a direction, and then a little bit more complicated to simulate gravity towards an object. And I'll be showing the latter part, to simulate gravity towards an object, by actually creating a class that gravitates every object of that class to every other object of that class to simulate gravity a little bit between them. But let's go ahead and get started with left and right. So let's say we want to simulate gravity other than up or down, and we want to do it with a box. So what we can do, or a cube or any other shape, what we can do is take a static mesh of whatever static mesh you want, and you can drag it out here, or you can start by creating a blueprint on your own. But I'm just going to go ahead and drag this out and hit the blueprint create button here, and I'm just going to call this test directional grav. Create blueprint. It doesn't need to be apparent or anything like that, so it's just going to be very basic. And what we're going to do for this is we're going to go to the static mesh component, and we're going to simulate physics, but we're going to turn the gravity off because we don't want to be using the Unreal Engine gravity. So when you compile and look at it, it should just be floating there. You'll note that the physics are on. I'll go ahead and stick it under this box here so you can see what happens. So no gravity, just floating box. And what we're going to do is go ahead and very quickly implement what will be the gravity. So if this screen comes up and it's just the defaults, you can always hit open full blueprint editor to get back to where you want. And this is one of the easiest things to do. I've seen a lot of forum posts that say it's impossible to set the gravity to a different direction unless you're editing the engine code, or you have to use C++. And that may be true if you intend on using the Unreal Engine gravity. However, gravity is just a constantly implemented, or a constant force impulse on an object. So And I don't mean impulse in the Unreal Engine way, I just mean it's a constant force applied to an object. So all we need to do is apply the effects of a constant force on this static mesh. And what I mean by that is, in the case of gravity, the effect is acceleration. So to do that, we're going to get the static mesh component, and we're going to set physics, set linear, set all set, oh god, there's so many of them, linear velocity for the static mesh component. Don't know why I did that. So once we have this pulled out, we're going to go ahead and hook this up to the event tick because we want this to happen every time it ticks. And because we don't want it to set it to a constant value, we want it to add. That's how acceleration works, is it adds per second, theoretically, but we'll be doing it per tick. You can also normalize the ticks. There's a way to do that, but I'm not going to worry about that. I'm just going to assume that the ticks are all going to be fairly consistent. And what we're going to actually do is change it to 9.8. Well, and I'll show you first. I'll do it on the z axis here. Minus 9.8. So that should be going downwards, and that will make this cube that we have here fall at roughly the same rate as everything else. And you should hardly be able to tell the difference. And that's all you need to do to actually simulate this gravity. If I duplicate it and create a few more, you'll notice that they all fall with the Unreal Engine gravity almost flawlessly. But it doesn't have to be 9.8 down or up. You can set the z value to 0, and you can set it to minus, or let's do it just plus 9.8, 9.8. I'm just using 9.8 because that's the gravitational constant on Earth, 9.8 meters per second squared. So if I do this, oh, look at that. There they go. And of course, they're still simulating physics, so let's go ahead and switch that around. Let's do minus 9.8 to go the other direction. They should hit some of these boxes. Yeah, there you go. They're still simulating physics. They have all of their angular velocities and everything still built in. No problem there. So that's very simply, you want to do physics gravity simulation in another direction other than up and down. That's how you do it. Very simple. I will give one caveat. If you do this with a character, you may run into problems with landing on what appears to be a surface. So for a game jam a while back, I did a game where the gravity could switch up or down and sometimes other directions, and the problem was that if you have, say, another surface that's up here, or even, you know, like over to the side. And remember, these can go diagonals too. You don't have to set it to left, right, up, down. You can set it to any diagonal you want. But the problem is that while objects will interact with this fairly normally, we've got one box stuck here, yeah. The character actually has like a on land event, and on land they like stick to the floor, and that smooths out any jittering that is caused by the character movement component when they move along. On land events, it's very difficult to allow a landing on anything greater than 90 degrees. That's the highest you can set the on land event, at least that I can find exposed in the engine. And even looking at the source code and trying to fiddle with that, I could not figure out how to do that. So if you're doing this with a character, just note that you may have to fiddle around. One suggestion is to turn off the on land, like just ignore it, and then set the character in a constant like swimming state or something like that. That's not going to trigger the walking state. But so that's that. Simple enough. It looks like, I don't know, 10 minutes in. Very easy to do. You can set this up in less than 10 minutes. So let's do something a little more complicated though. We don't want to just go left, right, up, down. Remember, we can set this to any vector we want. So instead of setting this manually, we're going to set this dynamically, and we're going to do it in a way that will allow you to very roughly, I'm going to give this caveat now, very roughly simulate gravity between a lot of bodies. I'm also going to give the caveat now, this is not a performant thing. If you do this between more than a couple dozen actors, you're going to probably crash the engine. So save and save often as you're doing this, but I will show you guys how to do it. So we're going to go ahead and create a new blueprint class, and it can be an actor of any type. Let's go ahead and call it Gravity Parent, and I'll explain why I want it to be a parent later, because we're going to extend this class so that you can have different meshes, different objects that are children but still have this effect. And I believe that Unreal has a pretty good support for multiple inheritance, so you should be able to have another class that has its own stuff, but that is also extends this gravity parent. If you don't know what that means and you just want to get things to gravitate towards each other, that is okay. So let's go ahead and open this up. And it's got a default scene root, which is good. And what we're going to do is we're just going to add, for now, static mesh. We're going to call this the static mesh too, as opposed to sphere. And I'm going to call it static mesh generally because with the children, you may extend this and then want to switch this static mesh out. Currently, this static mesh is a sphere. But if you extend this object to children that you also want to have gravity, you could make it look like an apple or an animal or anything else that you want. So what we're going to do now is something very similar. We're going to start by set linear velocity. See, it pops up perfectly now. And we're going to do this each tick again, so I'm going to go ahead and set it up in front. But before we do each tick, what we need to do is the dreaded for loop. And we're going to iterate over, but get all actors of class. You could probably also use an interface to do this, but since I'm actually including some logic here, it'd have to be an abstract or something weird like this. I'm just doing a class, and then we'll extend it as we need. Any programmers who watch this and want to let me know the best possible, most efficient way to do this, please do, because this is constantly an issue that I bump up against. What are we going to do with this? Okay, well, with this, we're going to go, for all of the output actors, we're going to do for each. And what are we going to do in each loop of this body? So each iteration in the loop body. So that means that if there's 10 of these guys, it's going to take the array of 10 of them, and then for the first one, it's going to do this. And then once it's finished with the first one doing that, it's going to go back and say, okay, what's the second one? And it's going to do this again, but on the second one. And once it's finished that one, it'll do the third, and so on. Once it's completed, then it'll execute this pin, which we won't actually be using at the moment, but you're free to use this to continue on your thread as you please. Just realizing that if this becomes very large, it might be a while before this is completed. So it may be useful if you have something that is needs to happen at the beginning of the tick to sequence this off. And to set this second and anything else important out of the first one, because these will happen sequentially. But it doesn't matter, because all we're doing is the gravity. Sorry for those tangents. What we're going to do on the loop body is set the physics linear velocity. But what are we setting it to? Well, we have here another element that we know already is going to be of this gravity parent class, because we're getting all the actors of that gravity parent class. And each of them is going to have a static mesh. So what we're going to do is we're going to get the location of that actor. And if you want to be more specific, what you can do is actually cast to gravity parent, and then you can, as gravity parent, get static mesh, and then you can get the world location of that. Since they're all spheres now, I'm not going to do that. So what we're going to do is we're just going to get actor location, and we're also going to get the static mesh. Now this static mesh is not this actor, this whatever actor we're on in the array. That's the local static mesh. That's this one here, for this one that's doing the calculation at the moment. What we're going to do is we're going to get world location for that guy. Okay. And we need a few things. So the way that gravity between objects works, and I'm just going to go over this quickly. If you just want to do it towards one of them, you can get find, look at rotation, and you can get the forward vector. I'll just go ahead and do this. We'll see what it does. I think it's going to be a little bit strange. Oh, I haven't put any in the world, so that's not going to do anything. Let's go ahead and put like a couple of them here. Yeah. I don't. Is it too slow, or are they not moving at all? Add to current. Let's go ahead and play. If you need to get out, you want to move your cursor around so you can look at these values while it's running. You can hold down the Shift key and then press F1. So we can tell that this is executing. And we can tell that the value that it's getting is not what you would hope. So you've got these two values. Oh, I know. Okay. It looks like we may need to find that rotation. I just did this previous to starting the stream. What is wrong? Play, Shift F1. Get forward vector. It's 170, 160. Well, it's reading both of them as the same. Oh, I'm sorry. Yes. Stop. You need to do an if. So we don't want to do this for itself. So if. So on this loop body, we're only going to do this in one case. And that is if it's not the case that this self is self. Get a reference to self, and we want to make sure that it's not the case that equals itself. And in the case that this does not equal itself, then we're going to go ahead and fire this on the particular element in question. Hopefully that'll do something. No, that's not going to do anything. Okay, well, that's not how gravity works anyways. Luckily, for us, oh, you know, another thing is, I am going to get the static mesh for this. Get cast to gravity parent. I didn't do this last time though. I didn't use a cast and it worked just fine. I'm not sure why. Well, just okay. Cast to gravity parent. So this will need to go. It can go after the tree. We don't need to cast every single. You don't need to cast yourself to the gravity parent. So what a cast is it's saying, hey, this reference that we have, I know what it is, even though the program doesn't yet know what it is, and it's a gravity parent. So we're going to treat it as if it's a gravity parent, and I'm going to, as a gravity parent, I'm going to run a function on it, which is the get static mesh. So if this fails, if the cast fails and it says, wait a minute, you just said that this is a gravity parent and it's not a gravity parent, this node will fire. Otherwise, this node will fire. And it will always fire because I already know that we're only working with actors of this class. As the static mesh here, I'm going to get the world location just the same as here. I'm going to do this, and hopefully, so this is getting a little bit messy, and I'm sorry for that. I didn't have to do this, and I think it's because when I did this last time, I created it the same way, where I created a blueprint from the object. But this should also work, so Shift F1. We should be getting, yeah, we're getting actual values here. I'm going to go ahead and close. They're still not moving. And that is because I am a fool, and I didn't set simulate physics, and I didn't turn off enable gravity. I probably don't need that cast. There they go. Oop. So now that's very, very basic gravity. Something interesting about this is that it doesn't matter how far away they are, and this might be what you want. It doesn't matter how far away they are, they're going to accelerate towards each other at a fixed rate. So you can actually set that fixed rate by multiplying this here. Multiply, it'll have to be a vector times a float, and you can probably set it to 9.8. And remember, you know, there's already positives and negatives baked into the 3 vector values, so you don't need to worry about doing negative 9.8 or anything like that. So these, there you go. Now those fall at the same rate as these boxes fall towards the ground, or these boxes fall sidewards, and they will fall towards each other, which is fantastic, but it's not physically accurate because in real life it turns out that the force between these two objects is calculated by the inverse square of their distance. So what we're going to do is jump in here. Oh, and I want to show you another interesting thing about this. Because it does it for all of these, if I put a third one in here, you get that. And if you put a fourth one, or even a fifth one, then you're going to get, yes, there we go. Oh, look at that. Terribly fake orbital mechanics. But that's how simple that is to do. And there they all are. And that's great, except for, like I say, this is completely unrealistic. Still cool, could be very useful. Depends on what you want to do with the game. If you don't care, if this is a platform or like multiple things that you want to have equal gravity, maybe like a Mario Galaxy sort of game, and you don't really care about any sort of physical accuracy, then you're set. And my guess is I don't need to do this whole casting thing. I'm going to take it out and see what happens really quick. It was not working, not because of that, but because I was stupid and hadn't set physics simulation on. It should have, I'm not sure, it's because it's a physics velocity, and it needs the physics simulation to be on for that to take effect at all. So what we're going to do is going to get world get actor location. Sometimes you have to type it in exactly like the engine wants. So this, again, you can do it either way with either the actor location or the static mesh location. It should be exactly the same, yeah. Pretty much. Maybe slightly different, actually. I'm not sure. Looks like we've got some almost stable orbits going on here. So yeah, we're getting a little bit different behavior, which is actually fairly interesting, considering I didn't change that much. So the actor location must be slightly different than the static mesh location. That's the only thing I changed now, is that this location is different. So the only difference in this is going to be that. Not sure, I'll have to play around with that. I apologize if you can hear the screaming people outside. That is one of the downsides to living in a city. The other downside is that the windows are open because it is about 90 degrees in here, which is why I have this gigantic iced tea. So I apologize for screaming people. I apologize if I look a little bit sweaty. The way that gravity actually works is going to be that you actually are going to do some vector math here. So let's do minus vector times vector. And what are we doing here? We are actually getting this vector that is a vector between this point and this point. And remember, this is a location and this is a location. So we're getting the difference for each of these values, and we're going to get the vector length. Notice there's vector length and vector length squared. I'm going to use that in a second. But so what you're going to do is you're going to get the vector length. And this is how you have it. The formula for the gravity is it's going to be, I wonder if I can do a comment. It's actually m times whatever your gravitational constant is over the distance between the two objects, obviously squared. Roughly. That's a Newtonian, that's close. It doesn't take into relativity, and however accurate your constant and other variables are in terms of locational positions, are going to affect how accurate this system that you're modeling is. However, to do that, we need the length squared. Remember, and we're going to set a manual constant. So what we're going to do is, instead of doing that, we're going to pull off length squared, and it knows that's the better one to use. So we're going to take this vector length squared, and we can consider this to be the gravitational constant, and this is going to be also have the directional data. We know that that's going to be the force, what I just mapped out, but it actually needs to be multiplied by this to get the directional data. So what we're going to do is we're going to do the division here, and it's going to be, we'll go ahead and do float divided by float, and we're going to pump in the vector length squared. It's already squared for us nicely down there, and we're going to set the gravitational constant right here. And I find that this constant actually needs to be very high, because when you're taking a length that might be several hundred unreal units and you're squaring it, it can be quite large. And when you take, if you were to do something like 1 divided by something like 400 squared, it's going to be some fractional decimal that doesn't do anything. So what you're going to want to do is to, I usually use something like 400,000. 1, 2, 3, 4, 5. Yeah, 400,000. And then we pump that into here instead of 9.8. And that's going to give us the constant. And what I am not including in here is actually that 400,000 should be moved out, and the masses of the two objects should be combined, and then the ratio calculated so that if they are two different masses, then the force between the two will be the same, but the acceleration of the smaller will be proportionate to the mass of the larger, and the acceleration of the larger will be proportionate to the mass of the smaller. These are all the same size. I'm going to assume they're the same mass. We're going to let m be 1. The ratio between the masses is going to be 1. So we're just going to leave it like this. And what that's going to do is actually make this look really like nothing for a while. But as they get closer, you'll notice that the acceleration speeds up. And you start to get a little bit wonky. There, that was kind of strange. I see that again. Yeah, that's very odd. I may have the subtraction backwards or something like that. It looks like I do. Something is, yeah. Let's try and switch this, because if you remember, okay, so this one is going to the top, so it needs to go to the bottom, and therefore this one needs to go to the top. Okay, so if you remember up here, I'm doing a find lookout rotation, and it needs to be directionally correct. So in this case, this one's going to the bottom, this one's going to the top. I think then the subtraction needs to be reversed. I could be wrong. You have to work out all the little details. So hopefully when they get closer, they're not going to do such strange... Well, same thing. Well, that's because the distance is actually the same when you square it out. So what are you doing exactly? What is happening? Well, let's take out all of the extras. Let's take them all out. I just want to see two interact with each other. Okay, that's what you would expect. Let's add a third and see how it interacts. Not what you would expect. Maybe this is a little bit overbearing. Let's see. Oh, that's because... I'm sorry. No, this is correct. Rotation. Get forward vector. So multiply the forward vector times that. Let's take out this. This identity thing was not in my original one. I was trying to do that to fix. Look at that. Okay. We're going to go ahead and slowly increment this. Let's start 400. Too much. 4. 2 orders of magnitude down. Look at that. What is happening? Get actor location. For each. Very odd. Not sure at all what's going on here. Find lookout rotation. Return values to rotation. Get the forward vector. And multiply the forward vector times. Let's try this. Let's try taking out this. Not sure what's going on here. Set physics linear velocity. Well, one thing that we can do is set a, under physics, we can actually set a linear dampening constraint. There should be a maximum, there's a maximum angular velocity. I would think there would be a maximum linear velocity as well. Interesting. Let me try and switch these two. See if that makes any difference. Nope, same thing. Let's see. I'm gonna go ahead and open up another project that I've had. Gravity Sim. Here we go. And take a look at the guts. There's a lot more in this, so beware, but hopefully glancing at my old blueprints will give me some insight into what I'm doing wrong now. I don't want to start completely over. I had this successful about 10 minutes before I started the stream. And somewhere in here I've messed something up. And I'm not sure what. 59%. Gravity parent. There's only one gravity parent, correct? Yep. Boy, oh boy. I can't wait for this heat wave to be over. It is toasty in here. There we go. Okay. Whew. Fixed planet, planet. Root object. Probably just planet. Let's go take a look at this. No, let's figure out what these are first. Build outliner. Planet. It is a planet. Okay. So let's take a look. Parent take. What is the parent? Inherited. Introduced in root object. Okay, it is root object. Oh, yes. Okay. Here it is. Find lookout rotation times the mass. Get the vector length. Up by power of 2. This is before they had that nice power node. Under gravitational constant and the mass. And then it comes up here. It splits it out for the other object and for itself. Distributing find lookout rotations. Well, an exit. Don't save. Here's what we do. I'm going to very quickly, without re-explaining everything I'm doing, I'm going to delete those. I'm going to delete this. And I'm going to start the same way that I started a few moments ago before I started the stream. And we're going to call this Gravity Parent. Create blueprint. I'm not sure why I was having such a hard time with that. We know we're going to get all actors of class, and then for each, oh, I do know why. Maybe. Loop body. I think it's because I was setting the linear velocity of... Oh no, that's right. Okay, so for each we're going to set linear set physics linear velocity. There we go. Static mesh component. Now what we're going to do here is that. And we're going to get actor location. We're going to get our own actor location. get rotation. I think that one needs to go down here. And then we're also going to do minus. Vector length squared. It's going to be on the bottom part of a division with, say, well, I'll start it at 1. I'm going to get the forward vector. We're going to multiply these. This should be as easy as possible, but multiply vector times float. There we go. Then drive that right into there. So that should be driving the new velocity. We'll make it additive, compile. Why not? Let's see what happens. What is this? That makes me nervous that that is there. Oh, that was the original one that I drug out there. Okay, that's fine. 1 is too low. It's not doing anything. But it also didn't disappear randomly. So that's good. 400. Let's compile that. Still too low. Didn't disappear though. Also a good sign. Let's try 40,000. Nothing's happening, and it's because, again, simulate physics, enable gravity off. Please don't fly off and just disappear now. Ew. Alright, 400, one more. 1,000. Shift F1. Nothing. Nothing. What's going on here? Oh. Boy. I really scare myself here. Losing my mind. Shift F1. What are these values looking like? Oh yeah. Look at that. These are nice positive values. Let's go ahead and get out of here. Take a look at these guys. What's going on here? Okay. That looks more like what I expect and usually see. Look at that. Let's spread these out a bit. Please don't do anything weird. No, nothing weird. Looks like I expect. Okay, I'm sorry about that. I don't know what happened. That is how to do that. This is a long video, so I'm going to go ahead and wrap that up. I'll run through this really quickly one more time. What we're doing is we're getting all the actors of this gravity parent class. For each of them, we're getting the fine lookout rotation that's going to get a direction from the one that we're talking about to the other one that we're talking about, whatever's near, whatever is us, looking at whatever element is in the ray. We're getting the distance between them, and we're squaring that. We're putting that squared distance on the divisor, dividend, the bottom of the division, and we're multiplying that times the directional data that's stored in this lookout rotation vector, and adding this every time it loops through to the physics velocity of what's at hand. What you might want to do actually also for accuracy's sake is take this linear dampening off so that we're not getting any weird like slowing down done by the engine that you don't want. But so that's that. The reason I had this as a gravity parent is that if you want, you can then create a child blueprint and call it grav child. And in grav child, you can actually then like take the compile. So we can make this grav child say like a cube, but because it's inheriting all the same functions and this cube is actually just labeled as static mesh, it's going to interact with these just exactly the same way. So now you can do like virtually any static mesh. The only problem we're having here, and why these are spinning off, is that the cube is actually imparting its angular velocity into the system. And the angular velocity is not included in the calculations of this system. So that's why spheres work really well, because they touch on one point. Cubes, not so much. So what you can do is on collision, if it's colliding with any other one of those, you can try and like turn the angular velocity off, or it gets tricky. No doubt, it can get very tricky. But that's a different problem for somebody else to solve on a different day. Thanks for watching. Thanks for bearing with me if you watched this whole time. 45 minutes is much longer than I intended for this video, but that is how it works when you're live streaming like this. So have a good night, and I plan on doing at least one more stream probably tomorrow on how to bring Vive controllers, how to get the Vive controller models into Unreal and get them working with the motion tracking of the actual Vive controllers. So you can take this controller and move it around, and the model that you import into the game follows along. Till then, have a great night, and I'll talk to you guys later.